opening words you want to say today, Herbert?
Yes, please, go ahead.
Okay.
So, again, same, you have the schedule, it's updated, it should be okay now. And we have slightly smaller audience, but because of traffic problems. So expect enough interest again.
Lovely.
Yesterday was a lot of fun. We had a lot of good feedback. So
Excellent.
continue in with the same spirit.
And I'm really looking forward to today. So good morning, Cape Town, South Africa. I'm happy to be back for part 2. Yesterday was sort of the fun laying the foundations of why are we talking about quantum field theory, how did we get here, and what are we going to do with it. Today, I think we get to really capitalize on some of that investment when we get to discuss what is a gauge theory, what does it mean to be a gauge theory, and what does that have to do with symmetry, and how does that ultimately give us QCD specifically. Before I get completely into the weeds, I sent out an email right before coming down to set up here in the classroom. I think some of you already received it, but just to make sure you're all on the same page, I sent out the specific PDF for the lecture notes that I'm going to talk about today, as well as a link to this overleaf page, which is where I have sort of all of the cumulative notes. That covers last lecture, this lecture, as well as what I've got blocked out for the next couple of them. You know, exact boundaries of where one ends and the other begins are subject to change, but you can take the link that I sent in the email and log in here, and you're free to look at sort of the whole track record of what we're working on now and what's coming next. No need to worry about that overleaf link. You cannot do any damage to the LaTeX code. It's a read-only link, so feel free to follow it and take a look at the overall lecture notes if you would like. That's cool. So, okay, as far as logistical things, I think that takes care of it. Now let me recap what we discussed last time. I sort of, like I said, tried to take not just a bird's eye view, but almost an orbital level view, starting with everybody's first baby steps with F equals ma and all the way down to the roots of quantum field theory. The main points that I stressed last time were canonical quantization, the generality and the importance of canonical quantization. Canonical quantization is a way of expressing a continuation of classical mechanics into quantum mechanics. Quantum mechanics doesn't come out of thin air. It's not a total, complete break with everything that we know about classical mechanics. There's a well-defined continuation of all of these basic concepts: coordinates and conjugate momenta, energy and momentum, angles and angular momentum. All of those fundamental quantities don't end with classical mechanics. They carry over in this very specific way. And that very specific way is algebra. This is a theme that comes up in quantum field theory over and over again, the primacy of algebra as the unifying theme. That will definitely be the message today for gauge symmetries. In the context of canonical quantization, that algebra was the algebra of the brackets. The classical mechanics worked with Poisson brackets. Quantum mechanics works by commutator brackets. But those things have exactly the same algebraic properties, even though they're very different objects from each other. And that's what makes it possible to ever have a well-defined classical quantum correspondence, such as Ehrenfest. And the point is that this is much more general than just the specific example that we worked out. This governs time evolution. This governs spatial translations. This governs every canonical symmetry transformation and its mapping from classical to quantum mechanics. So this is a very robust coat rack to hang your hat on, so to speak. And that was what brought us out of single particle quantum mechanics and into quantum field theory. Going quickly to the limits of what one can accomplish with a finite or a fixed number of particle theory that is supposed to be relativistic. As soon as you take quantum mechanics and you let it talk to relativity, all kinds of complications start popping out of the box. And the thing that quantum field theory solves for us is the problem of making a theory that is explicitly relativistic, explicitly causal, and fundamentally multi-particle quantum theory. Once we started talking about quantum field theories, we said the simplest quantum field theories are free theories. These are theories whose equations of motion are linear. And that means they satisfy a non-interacting linear superposition principle. So you can think of the non-interacting free quantum field theories as defining what are the possible free particles that could exist in nature? And the miracle of it is, once we know the algebra of special relativity, the Lorentz group, it is possible to enumerate, to just sit down and list every single possible representation that can ever exist of special relativity, of the Lorentz group. I find that particular bit to be one of the most profound lessons in all of physics. When I teach it to my students in class, I say, with this we have constrained God. This really means that the principle of symmetry is so strong that the only particles that can exist in nature are the particles that exist in one of these representations that are consistent with that symmetry. In terms of a quantum field theory, the transition from classical to quantum happens exactly the same way that it did with canonical quantization for the quantum mechanics of fixed particle number. We take Poisson brackets defined in terms of the field itself and its canonical field momentum, and they get promoted to quantum commutator brackets in exactly the same. So it's all unambiguous in its prescription. Once we have the free theories, now the fun begins, and we want to understand what's out there in the landscape of interacting quantum field theories. And that's the subject of the topic for today, and that was where we left off last time. So before I wipe the board and start with some new material, are there any questions or comments from the discussion from last time? Okay. Okay, I talked about the first of these examples last time, but the discussion that I want to have before diving into full-fledged quantum electrodynamics is a discussion about perturbation theory and its limits. Now, far be it from me to knock or rag on perturbation theory. Perturbation theory is a fantastic approximation strategy. It gives us a controlled basis with which to approach difficult nonlinear problems. But perturbation theory is far from complete, and it has both pros and cons, places where it succeeds and places where it fails. The reason that perturbation theory is the starting point for all of our discussions, its most important pro, is that it is a controlled approximation scheme. If I'm working in QCD and I do a calculation to a particular order in the coupling constant alpha s, then that means my error is one order higher, alpha s squared. That's the power of perturbation theory. You can always estimate how large your error is because there's a governing principle that organizes what terms you keep and what terms you don't. So we left off last time with the first of my counterexamples of places perturbation theory can fail. Rather than sketch that again, let me simply just point to it on PDF. Here we go. So this was this example of the binding energy of a Cooper pair, the BCS mass gap, which has this characteristic form of an essential singularity, exponential of -1 over the coupling. And that particular form, as illustrated here, goes to 0 very, very strongly from the positive real direction. From the negative real direction, it blows up catastrophically to infinity. And in the complex plane, it goes wildly in between in phase. This essential singularity is one of the most wacky things that can happen in complex analysis. And for our purposes, the important part is that it has no weak coupling expansion. If you attempt to expand this physics in terms of a power series in the coupling constant, you get identically 0. So this physics, which is fundamentally non-perturbative, has no perturbative representation. So that's the first example of places perturbation theory can fail. There are simply some effects that are genuinely non-perturbative. And the characteristic form of this is something e to the minus 1 over alpha, if alpha is the corresponding complement. Here we saw in the example of the BCS mass gap, something very similar happens in QCD with the spontaneous breaking of chiral symmetry that takes you from almost massless quarks to the entire mass of the proton just by the energy of the self-interactions of QCD. So that's the first downside of perturbation theory, places that it can fail. Let me again just jump to the PDF so that I can point at a figure rather than drawing things on the screen. The second dirty little secret about perturbation theory is that often it does not converge. That's the little fairy tale that we like to tell ourselves when we start to formulate the perturbation series, to say, I'm going to do a calculation to leading order, next to leading order, next to leading order. But I know in my heart that if I just work hard enough and I calculate 1 more order in perturbation theory higher, or 2 more orders in perturbation theory higher, that just with a little elbow grease, I can improve the precision of my calculation arbitrarily, if only I'm willing to put in the effort. That fairy tale is false, and that is demonstrated here in this example of an asymptotic series. So what's shown here is a particular function f of lambda as a function of coupling lambda. That integral is shown here. This is really just an illustrative example, but you can sort of see the ingredients. The integral looks like the action. It's similar to integrating the time from minus to plus infinity. Here you see something which is Gaussian. That part you can integrate exactly. And then you have a non-linear interesting piece here that looks like maybe a 5 to the 4th theory type interaction. What's being shown here in this plot is a comparison between the exact numerical evaluation of that integral for arbitrary values of lambda, that's the curve shown in black, versus if I did a series expansion in this coupling constant lambda. I could expand that to 0th order, 1st order, 2nd order, order by order in the coupling lambda. Then I can do the integral. Since that's a Gaussian integral, you can even do it analytically. So this is a comparison of what you get if you compare the exact analytic solution, or say the exact numeric solution here in black, versus the result if you tried to calculate it in perturbation theory. So here the dark red is n equals 2, 2nd order. And then if you go to next to leading order, that would be the blue, n equals 3. And then you have the brown, the green, and so on and so forth. We would like to believe that the series is convergent. If the series was convergent, then we would see that as I go to higher and higher orders, that these curves get monotonically closer and closer to the true answer. But that's not what we see. What we see is instead that they get closer for a while, and then they start to get worse. So if I compare next to leading order, which is the dark red, n equals 2. When I go to next to leading order, n equals 3, they do get a little bit closer together. And the agreement does persist out to a little bit larger values of the coupling. But then when I go from n equals 3 to n equals 4, I really don't see much improvement. The n equals 4 deviates from the n equals 2 around here, and it doesn't seem to really be getting any better. And from n equals 4 to n equals 5, that breakdown happens even earlier, and it's actually worse than lower order calculations. And if you push it to something really high, like n equals 10, then the breakdown happens incredibly early, and the entire thing is useless. So when we're talking about what perturbation theory can and cannot do, that is one absolute skeleton in the closet that we have to confront, which is that most of the time, the perturbation series does not converge. Most of the time, it is an asymptotic series where it gets better for a while, but eventually, even if you could put an infinite amount of hours to do all of the work, it wouldn't help you because your answer would start to get further and further away from the truth. So that is one very important caveat to keep in mind about perturbation theory. That is that it is not convergent. It is generally an asymptotic series. So those are two things that can cause perturbation theory to break. These non-perturbative physics effects, we said, are generally the result of a radical change in degrees of freedom, something like a phase transition, where there's a sudden non-analytic breakdown in how your degrees of freedom behave above the scale and below the scale. But one thing that perturbation theory can do well is describe a slow transformation in its degrees of freedom, not an instantaneous radical transformation, but the change from a bare electron to a dressed electron, or a dressed electron to a more dressed electron. As long as that change in degrees of freedom is slow, perturbation theory is capable of correcting itself. So it is possible to do self-correction in perturbation theory through resummation strategies. And so that's what I want to talk about next, which is leading logarithm resummation. Question, yes?
Sorry, just to go back to the example that you showed of the convergence breaking down.
Yes.
I'm just a bit curious, what makes the infinite series actually converge then, if we see this divergent behavior in the first few terms of the power series?
It's a good question. I don't know that I'm qualified to give you a thorough answer. I think the strict answer is that the series representation is divergent, that there is a correct answer, but that it is not possible to, by normal techniques, explicitly sum the series and recover the true answer. There may, however, be more advanced, more modern series techniques that are built for handling divergent series. I am no expert in this myself, but I know that there exist techniques related to Borel resummation that give controlled ways of discussing divergent series and their properties. So perhaps that would be one way of quantifying that divergent series.
So in this particular integral, you can actually see explicitly by looking at the integrands of the expansion, why this diverges, right? Why it gets bad. What you have is positive powers of y to the fourth that appear multiplying the Gaussian. And what you see is that the peaks of this gets above double hump, and this moves further and further out to large lambda values. And if you look at the integrand of the unexpanded thing with the y to the fourth term in the exponent, you see that it actually makes the support of the function narrower, right? So you're pushing against what the real thing is. You expand something, right? But the problem is you expand something. So it's a typical thing of expanding things under the integral instead of expanding the result of the integral. So this is a typical issue there, and it's the same thing.
An outstanding discussion, Herbert, in front of the board for the TUTS.
Absolutely, that one should look at in the TUTS.
So I don't mean to cut off any discussion. Are there any other questions or further comments on this? Okay, great. Thank you for the question. So I was commenting on this idea of resummation, specifically leading logarithmic resummation. So let me motivate where this comes from. Normally, when we're doing perturbation theory, the idea is that I'm doing some expansion, that I have my function like my cross section, and I write the thing as a power series in the coupling. So I would say I have d sigma 0 as my 0th order, and then I have, let's say, alpha s times the first order correction plus alpha s squared times the second order correction, and so on. That's my normal picture in perturbation theory. And as long as my coupling constant is sufficiently small, then it should be the case that every higher order is much smaller than the one that came before it, and that's my justification for truncating the series at any desired order. This all sort of operates on the fiction as if the series was convergent. But even if it's not convergent, it still works this way for at least the first few orders in perturbation theory before that breakdown really gets severe. This is sort of the normal power counting. But sometimes it happens that in addition to this coupling constant, that there's something systematic that starts to show up in your cross sections. That something systematic is usually associated with a phase space. So this happens all the time in quantum field theories when you have a wave function that describes a quantum splitting. So for example, I can have a particle like a quark or an electron that comes in and then it undergoes an interaction that causes it to radiate a photon. For this purpose, it doesn't matter whether it's a quark or an electron. I could equally well make it a gluon for the quark. The point is that there's a wave function that describes that probability of the incoming electron to split into the photon plus electron pair. The general form of this wave function, the details change depending on your theory. But in general, what you get over and over again coming out of these wave functions are integrals of the following form. You often see them in a way that looks like alpha s, that's the coupling constant that you pay for having this interaction at the level of the probability. You get an alpha s, and then you have an integral over the phase space of where that gluon or that photon could possibly be emitted. And often what happens is you get an integral over the transverse momentum. Let me write integral dkt squared over kt squared. That sort of 1 over kt squared form is the characteristic long wavelength behavior of these wave functions. So the details of the wave function can change, but they pretty much always go like over kt squared at long distance. And that means if I have an integral over kt squared and a 1 over kt squared, this integral is logarithmic. And that means I have to pay attention to what my limits are. I can't just put 0 to infinity because then I would get infinity. It doesn't make any sense. I have to have some upper cutoff, which is usually set by the kinematics of the process. It's the total energy, it's the total invariant mass, or maybe it's the total virtuality Q squared, such as in deep elastic scattering. And then I have some sort of cutoff that describes the lower limit. It might be a renormalization scale. It might be a result of an approximation where you assume that your momentum is much larger than the mass is. The point is that this 1 over kt squared dependence has some finite limits. And when I integrate over that phase space, I do get my alpha s that is always there for the power counting and perturbation theory. But I also get a logarithm of q squared over mu squared. And if this logarithm is not small, then that means that I can change how big or how small this coupling constant is, as long as it gets systematically multiplied by this. So if q squared is much, much greater than mu squared, then that log can start to become big. But I should emphasize it's not enough to have q squared bigger than mu squared. I need to have q squared exponentially bigger than mu squared. I need to have the logarithm of q squared over mu squared, much, much greater than that. But if I have this process, then that means that every time I branch and another photon comes off, if I do it again, I'm going to get another alpha s for the low probability to emit, but then I'm going to get another integral over the phase space. So I'm going to get another log every time I do this. So this log is not a one-off thing. It's something that appears systematically here as a result of the phase space integration. And if that log is large, then that starts to offset the smallness of the coupling constant. So you get to a tension where you can have the coupling constant can be small as you want. But if that log is large enough, you can always get to a regime where the product of the two is not small anymore. When this product becomes order 1, now this philosophy is broken. That's an example of a formally NLO correction that should belong here that is now so enhanced by a very big log that its contribution is more important than NLO. Its contribution is equivalent to leading order. So this large logarithm is potentially dangerous. It could spoil or destroy your perturbation series. Before I show you the solution, let me show you the other typical case where these things occur. This is a transverse logarithm. This is what you get when you have hard back-to-back splittings. This is characteristic of deep lap evolution, for those who are familiar. The other case is the one where you get the logarithm from the longitudinal variables. You integrate, let's say, dz over z, where z in this example would be the light front momentum fraction. If I have, let's say, momentum p plus coming in, then the photon might carry out a fraction z p plus. I believe Thomas already discussed light front coordinates in his lecture. If you're not familiar, just think of this as the energy. It's essentially the same thing for our again, this integral is logarithmic. Typically, if this is a momentum fraction, the fraction can go up to 100%, but there's some lower cutoff that limits how small it can get. Typically here it would be something like mu squared over q squared or mu squared over s, the Mandelstam invariant. And again, this gives you a logarithm in exactly the same way. So the point is that systematically large logarithms endanger your power counting for the perturbation series. But these logarithms don't happen by accident. They don't happen chaotically. They only happen as a result of certain systematic effects in that phase space integration. So this is something that we can actually capture and control. The way that this is generally handled is you write your cross section as a differential equation. You want to say, how do I generate this log? So typically you'll write it as the derivative with respect to that log of your observable, let's say d sigma in this example. And then you'll get something which is the coupling constant that tells you the probability, and then you have typically some integral. Don't stress the details, we'll see it in specific in a lecture or two for the case of the BFKL equation. But the point is that you can identify where the logs come from. And then if I can write it down as a differential equation that tells me I get one log for one alpha s for one step of branching, then if I solve this equation, the solution to this equation includes all of these effects. It would be the exact solution to this constraint, requiring that you have all orders of alpha s and all orders of. So this is essentially the idea of resummation. That when this quantity is not small, I have to add up all possible powers. So that means I have one is of the same order as alpha s log. That's also of the same order as two alpha s's with two logs. And it's the same no matter how many of those powers you have. So if I resum these things, meaning I systematically take into account the effect of all of these logs, then I have captured all of those most important branchings that make these contributions systematically enhanced. So this is the other pro, I would say, of perturbation theory. This is sometimes referred to as quantum evolution. This describes how the perturbation theory gradually changes as you see a new large scale, like this large logarithm, emerge from that. So if there's something radical that happens, then your perturbation theory is going to snap. But if the evolution of your degrees of freedom is slow and smooth and continuous, then perturbation theory is capable of describing how it should change itself to accommodate those evolving degrees of freedom. So the second type of logs, the logs of dz over z, these are the ones that are going to give rise to BFKL evolution and ultimately to gluon saturation.
Sorry, I have a question.
Yes, please.
So this mu in the log, if I'm understanding correctly, that's a renormalization scale.
Yes, that is typically how it correctly enters. The way that I've illustrated it here, you can think of it more like a cutoff.
Okay, so is Q a different cutoff then? So we have these kind of competing. I'm just trying to figure out why we can't set mu arbitrarily large if it's just a renormalization scale. Or arbitrarily close to Q in this case, make the log arbitrarily small.
So it depends sort of what theoretical framework you're using to set this up. So if you set it up in terms of a PDF, then you would say, I start off with a distribution at one scale mu, and then I calculate one perturbative splitting on top of it to find the PDF now at a higher scale q squared. And then I would end up with an integral that runs between the original scale mu squared of the PDF I began with up to the scale mu squared of the PDF that I'm evolving to. So in that renormalization scale point of view, this is describing the evolution of that scale from your initial scale to your final scale of choice. You can equally well describe, at least at the level that I'm talking about it now, you could equally well think of it as just a cutoff on the momentum integration. For instance, typical values of that scale would be something of order the mass. Why? Because if I have massive particles, then my denominator looks more like k squared plus m squared. And the logarithmic part of this is the part where k squared is much bigger than m squared. So I approximate k squared much bigger than m squared, and my approximation is only valid in the limit where k squared is much bigger than m squared. So I set the lower limit. So I would say you can think about it equivalently here. The most technically correct way to think about it is in terms of this RG evolution, as you say. For my purposes here, I think you can consider it just a cutoff, or even, let's say, a typical scale that's used in the approximation to pick up the logarithmic region. Does that answer the question? Okay, great. Okay, lovely. Those were the last of the comments that I wanted to make about perturbation theory and what it succeeds at and what it fails at. It is a fantastic tool, but it is remarkably incomplete. And it's important to always keep that in mind. Okay, so the main thing that I want to discuss for you today is the meaning of gauge symmetry. In order for me to do that, I have to spend a significant amount of time now discussing the scalar polarized mode of a vector plane, because that's entirely what gauge symmetry is about. Gauge symmetry is an elegant, beautiful way of killing the unphysical scalar polarized modes that are possible to have for a vector boson. So in order to set that up and explain where this comes from and what it does, first I'm going to start with something a little bit out of left field, which is the massive vector boson. That deals with this problem of the scalar polarized mode in a very different way, but it will help me illustrate what I'm talking about. So the goal here is to discuss what is the problem with vector bosons. And how do you get around that problem, at least for the massive case? The problem, in short, with the vector bosons is the existence of the scalar polarization. The scalar polarization is also sometimes referred to as the time-like polarization. Sometimes you'll see it referred to as the longitudinal polarization, but that's highly confusing whether you're talking about 3 or 4 dimensional longitude. I will refer to it always as the scalar polarized mode for reasons that will become clear shortly. The problem is that this potential mode of a vector field mu is unphysical. As we'll show, if I could have a mode like this and I try to quantize it, I'm going to get a state of my theory that has negative probability density, it has negative measure. And if I have this, this is completely incompatible with my quantum field theory. Incompatible with QFT. At minimum, I must have a well-defined Hilbert space. The one thing that the Hilbert space must have is positive definite norms of vectors. And this fails that criteria. So I want to show you what the scalar polarization is and why it fails so dramatically, so that then you can understand what it is that the massive vector field does to get rid of that. And then what happens when we take away the mass. And then we have to get rid of that scalar polarization in a very different way. Okay, that's the point. So with that in mind, I want to show you the example of the Croca-Lagrangian. The Croca-Lagrangian is for a massive vector field. So the form of the Croca-Lagrangian is -1/4 f mu nu plus 1/2 m squared a mu nu. Where here f mu nu is the field strength tensor. This is a generalized version of the curl. Compared, of course, to the idea of curl of A in 3-dimensional mechanics. So you would have dij with the anti-symmetric epsilon ijk. Same thing, you have anti-symmetric combinations of derivatives, but in 4 dimensions. That's the field strength. The equation of motion for the Procca-Lagrangian looks similar to Maxwell's equations. It is d mu f mu nu plus m squared a nu equal to 0. Or if you rearrange the terms, this is the same thing as d mu plus m squared a nu minus d nu of d mu a nu equal to 0. So from this form, we immediately recognize the Klein-Gordon operator. And we've also got this extra piece sitting around. It may not be obvious, but the Procca equation of motion implies a constraint. If I take this equation of motion and I hit it from the left with d nu, the divergence operator, when d nu hits a nu, I get divergence of a. And then this is box of divergence of a plus m squared divergence of a. And then when I contract d nu with d nu, I get box. So when I multiply by d nu, this term is going to cancel this term. And my equation of motion tells me m squared a mu equals 0. And since for this theory m is a positive number, it's not 0. This immediately, d mu a mu. This immediately implies d mu a mu is equal to 0. This is a constraint condition that is implicit in Procca's equation of motion. Once I know that this is a constraint equation, then my second term actually goes away and I just get the Klein-Gordon equation. So once I have this equation, my Procca equation of motion is just Klein-Gordon plus constraint. And it's that constraint which is the whole heart of the story here. By the way, I can immediately now write the general solution because after I plug in this constraint, I just get the Klein-Gordon equation. So I know the solution to the Klein-Gordon equation. The general form is a mu is sum over all polarizations that I'm allowed to have. And then I have an integral over the on-shell plane wave modes. For the vectors, they have creation and annihilation operators that come along with polarization vectors. And the key question is now, what polarizations can I have? A priori, without thinking about anything else, I would say the first expectation is that I should have 4 possible polarizations. Why 4? Because this is a 4 vector. And that means these polarization vectors are supposed to be a basis for that 4-dimensional space. So I would expect that I should have 3 space-like vectors, like I hat, j hat, k hat, and 1 time-like vector, like t hat, if you like, the unit vector in the time-like direction. 1 time-like, 3 space. And indeed, for the massive theory, you would have all 4 of those, except for this constraint condition, which kills one of those polarization modes. It specifically gets rid of this one, the time-like or scalar mode. So if I take this equation and I apply d mu a mu equal to 0 to it, I hit the left-hand side with the derivative. When I hit the right-hand side with the derivative, I bring down a factor of k mu, and k mu multiplies my polarization vector epsilon. So this condition, that constraint condition, tells me that I have limit on my polarization vectors. So the condition that comes out from d mu a mu equals 0 is k mu epsilon mu equal to 0. So, or in other words, k dot epsilon is equal to 0. How can I see that this is a time-like mode? Because this is supposed to be a massive particle. So I can always go to its rest frame. In the rest frame, k mu is a unit vector, k mu is just the mass times a unit vector in the time-like direction. So in the rest frame, this would tell me that epsilon has no time-like component. If it's not the rest frame, if it's a moving frame, then my epsilon here is parallel to k, but it's still time. So by convention, you can choose to describe this time-like polarization vector that we are excluding as epsilon k, and I'll write scalar polarized mu is I k mu over m, which in the rest frame is just, I 0. So the point is that the massive vector field comes from the start with a constraint condition, and that constraint condition entirely tells you that you've got to get rid of the scalar mode. And that's just a requirement for dealing with the massive theory. Why do I keep calling it the scalar mode? Because if I take that particular polarization vector here, something which is in the direction of k mu, and I plug it back into my definition for the free field, so I have a k lambda, the polarization vector is I k mu over m, e to the minus I k dot x, plus a k lambda dagger, minus I k over m, e to the plus I k dot x. And I realize that I can get both of these terms, this I k right there, I can get it from a derivative on the I k up there. And similarly here, I can get that minus I k from the derivative here. So I can write this expression as just minus d mu over m acting on e to the minus I k dot x. And likewise here, I can write this as minus d mu over m acting on e to the plus I k dot x. And then I can pull this derivative outside. So what I get is minus d mu over m, and the thing that I'm taking the derivative of is the integral over the on-shell phase space. This is now just the scalar polarized mode. So I guess I should say scalar and scalar. E to the minus I k dot x plus a k scalar dagger e to the plus I k dot x. And this object right here in the big parentheses, that is the expression for the Klein-Gordon field. That is a scalar field. So this object literally reduces down to the gradient of a scalar field when it is in this polarization. So this is what this means, this particular strange time-like mode that is explicitly forbidden in the massive theory. That mode is the mode in which a mu is the total gradient of some scalar field. So it kind of makes sense why this is a dummy mode of the theory. You're not really doing vector field dynamics here. It might look like you have a vector, but that vector is just a derivative. You're really doing scalar theory at the end of the day. So that is the scalar mode and what it looks like. Why is it a problem?
Sorry, can I just ask a question?
Yes, please.
I don't think I'm fully sure how. So was it because we chose to be in the rest frame that we can now we were able to get rid of the sum over the polarizations by choosing this specific scalar polarization?
You mean here?
I understood that.
No. Here I'm just by hand saying, what does A mu look like if it is in the scalar polarized mode? So in general, A mu would be a sum over all of the allowed polarizations. So maybe the better way that I should say it is, after I include all of these conditions, for the massive theory, I should have sum over all the polarizations, which are only the 3 space-like.
Okay.
And then I have the integral over k, a k lambda epsilon k lambda e to the minus I k dot x plus times. So in general, before you incorporate the constraint, you would say this sum over polarization should have all 4. Then you realize that the constraint condition removes one of these. So the actual expression for the modes of the massive theory are as a sum over the 3 physical modes, the 3 physical polarizations. Those are positive helicity, negative helicity, and 0, right? The 3 polarizations of the massive state. The thing that I'm illustrating here is the mode that's been left out. So the thing that we have removed by enforcing that constraint so that we can see what is the nature of that mode. Any other questions at this point? Okay, cool. So that's what the scalar polarized mode is. Why is it so bad? The problem is when you start trying to put it into a canonical set of commutation relations. What do I get if I take these Praga equations and I run them? When I try to quantize them for the Praga theory, I end up with an incomplete set of canonical commutation relations. Incomplete set of commutation relations. Precisely because of that constraint. I get commutator of A mu of x and t with the canonical momentum pi nu of y and t is I g mu nu delta 3 of x minus y if mu and nu are both space-like. But if either one of them is 0, mu equals 0 or nu equals 0, then I just get 0. This is a consequence that follows directly from this condition d mu a mu equals 0. It immediately leads to the fact that the canonical momentum pi 0, the 0 component of it vanishes. That's why I've got a 0 here, because there's nothing dynamic to plug in here for the momentum. That mode is not dynamic, that mode is constrained. So I don't have a full set of commutation relations because of that constraint. But you can see sort of what the picture looks like if you did put that scalar polarized mode back in. Right, it's obvious here what the scalar polarized mode did. It created that 0 when I took it away. If I put the scalar polarized mode back in, I would have all of these. I would get this expression for all mu and nu. And that's fine. But there's one important difference between this object, g mu nu, between when mu and nu are space-like and time-like. The difference is G00 is +1, but G11 and G22 and G33 are all -1. There is a sign change when I go from the space-like polarizations to also include the time-like. That sign change here is the one that's ultimately going to be responsible for those negative norm states that are in my Hilbert space. So for the constrained theory where you don't have the scalar polarization, you get this incomplete set of commutation relations on A and pi, And that translates to an incomplete set of commutation relations on the creation and annihilation. So this gives me delta lambda lambda prime 2 pi cubed 2e delta 3 of k minus k prime, but only if lambda and lambda prime are space-like polarizations. In this setup, the question of the scalar polarization doesn't even appear because the scalar polarization doesn't show up in the constraint. But if I put it back in, which is exactly what you do if you're doing gauge fixing, for example, then I get exactly this complete set of commutation relations with the full the full metric tensor G mu. And in the same way, that Kronecker delta, which is +1 if lambda equals lambda prime is space-like. When I put the scalar polarized mode back in, I get that -1 if lambda equals lambda prime is time-like or scalar. And that's the thing that kills it, because it means that the commutator of the scalar creation and annihilation operators has a negative value. So I get, I think the way that I should, I guess, let me pull in just the minus. Minus 2 pi cubed 2ek delta 3 of k minus. This minus sign kills everything. Because now if I define something that is created by these creation operators, so let's say I define a photon state gamma that has momentum k in the scalar polarized mode. I define it as just a superposition of plane waves, d3k, 2 pi cubed, 2ek. Some wave function, I don't even care what it is, I'll call it 5k. And the state is whatever I get by acting on the vacuum with my scalar creation operator. If this is a state that I construct by using that creation operator, then I just calculate the norm of that state, and I get something negative. So if I calculate the norm of that state, I get integral over k. I get integral over k prime. I have two wave functions, phi star of k prime, phi of k, but the important part is that I've got the operator bracket ak scalar prime, ak scalar dagger 0. Once I put these between the vacuum states, now I replace this product of operators by its commutator because the other term is 0. And when I replace this, I get minus 2 pi cubed 2ek delta 3 of k minus k prime. The delta function does exactly what it's supposed to do. It kills one of the integrals, but the problem is that minus sign is there. So I'm left with minus integral d3k over 2 pi cubed 2ek phi of k squared, and it's just something negative. So this is the kiss of death. This is the part where the scalar polarized modes are shown to be unphysical. Any theory that continues to have scalar polarized modes in it is broken. So this is the problem with vector bosons. This is true anytime you want to have a vector boson. You can't define the photon. The photon does not exist unless you solve that problem first. If you have a massive vector, then you solve that problem explicitly by demanding it as a constraint. But if you do not have a finite mass, then your constraint condition goes away. Remember that the constraint that came out of the Kraka equation of motion that condition was m squared d mu a mu is equal to 0. So as long as I have a massive theory where m squared is not equal to 0, it immediately follows that d mu a mu equals 0 and I'm safe from the scalar modes. But if the mass is equal to 0, then this condition is trivially satisfied. 0 equals 0. And then it appears that now my protection against the scalar mode is gone. And it seems that a massless vector theory will be contaminated by these unphysical scalar modes. That's where gauge symmetry comes in. Gauge symmetry is the solution to this problem. It is a beautiful way of making these scalar polarized modes unphysical in a different way, not by demanding it as a constraint, but by turning that unphysical mode into a symmetry transformation, such that it has no physical consequence because it leaves the Lagrangian invariant, or at least the action invariant. So that is what we will show now. Let me pause for a second before we get ready to dive in. What questions or comments do you have?
So maybe.
Okay. Yes? Yes, please.
Yeah, so you're really emphasizing that the negative norm is the sickness, if I understand you correctly.
Yes.
So why do you think that that's a sickness?
Because it is contrary to the axioms of the Hilbert space. That's the most concrete, tangible way that I can say that it is unphysical.
But does that mean, so physics is whatever physics is, why is it necessary that it has to be in a Hilbert space? Right, so I guess what I'm driving towards, right, is ultimately quantum mechanics, we're going to demand that probabilities are positive.
Yeah.
And that measurements are real numbers. Is there something inherent in a negative norm that leads to unphysical predictions from the theory?
I mean, essentially, I think if you start letting negative probability run around in your theory, you're going to get all kinds of contradictions. You can probably get, what, unbounded positive plus negative probabilities that can do crazy things. I think if you start allowing that, then everything is going to fall apart in wonky ways.
But the norm is different from the probability, right? The probability is an amplitude modulus squared. And then your negative number becomes positive.
I mean, I hear the distinction that you're raising. I don't immediately have a better answer for you.
I think maybe you, instead of thinking about probabilities as squares of amplitudes, you could be thinking about expectation values of operators in a quantum state.
Very good.
And so here that means that there's an identity operator has an expectation value -1. So you have.
Okay, but if I want something like, you know, what's the energy of the field, right? It's something in the field, something that's measured. I think those. Yeah, that's, if you see something that's say complex there, then I would be very concerned.
I'm not sure I heard everything in the discussion. It sounded like expectation values of operators, maybe another way to put it.
Yeah, so if one is an unphysical expectation of the operator, I would agree with that.
I would think that when you calculate the expectation value of the Hamiltonian in such a state, you will see that it's a negative state. So you have a scalar polarization state with a positive well-defined momentum, and you will have a negative energy.
Yeah, so I know, and maybe this is getting a little.
Yeah, very good, of course, because your physical observables are diagonal in the creation and annihilation operator basis, of course, so that your total Hamiltonian is integral over the modes, and then you would have sum over all polarizations, a dagger. So yeah, I guess if you take the expectation value of this for the scalar polarized mode with that negative contribution. Oh yes, sorry, times the energy here, or if you wanted the momentum, then you would have the momentum here. But yeah, it seems like the same problem, that as soon as I start sandwiching this thing between vacuum states, that I can get negative numbers here that would then inherit as negative energies or negative momentum.
No, I think that's cured again because you have to sum of the polarizations lambda, so there'll be a lambda mu or whatever like that, lambda prime. You'll have eta lambda prime, which comes in with exactly the right minus sign to save you. But I think this is an offline discussion. I don't want to fail everything. I wondered if there was
Interesting questions for sure.
Yeah.
Okay, cool. So now let's go to the elegant solution of gauge theory. Let me start by way of example, by writing down the most successful Lagrangian in history, the Lagrangian of quantum electrodynamics. That contains the free Dirac field, psi bar IV slash minus m psi. It contains the free photon field, minus 1/4 f mu nu, and it contains the particular interaction vertex minus e psi bar gamma mu psi a mu. So the anatomy of QED is that it contains free fermions, which are typically taken to be electrons, but they could be anything you want. It has free photons, and those are in particular massless vector bosons. And this is dangerous because it appears that these may be susceptible to the unphysical scalar modes. And then we have a particular interaction vertex. It may not be obvious when you first see it, but this particular form of the interaction vertex is very, very special. This is chosen in a very unique way, such that for this particular form of the interaction vertex, then these scalar modes become a symmetry transformation on the overall Lagrangian. That is what a gauge transformation is, what gauge symmetry is. So how did we come up with this particular form of the interaction vertex in QED? It starts from here. It starts from the free Dirac Lagrangian. Before I had any photon at all, so without any photon kinetic energy, without any photon interaction vertex, before all of that, I still had the Dirac field. That's psi bar IV slash minus m psi. And the point is that this Lagrangian has a beautiful continuous symmetry. That symmetry is a U1 complex phase rotation. Which means I can take the field psi of x and transform it to a new psi prime, which is the old field psi of x times a complex phase, e to the I theta, where theta here is constant. If I perform this transformation on the field psi, and I perform it on psi bar, then obviously this is an invariant symmetry of the Lagrangian, because I'm going to get e to the I theta here, I'm going to get e to the minus I theta there, and they're just going to cancel each other. As long as theta is a constant, there's no problem. This is referred to as a global symmetry. And that's because of the fact that theta is a constant for this transformation. The free Dirac Lagrangian already has this symmetry latent in it, just sitting around. Well, I guess it's not just sitting around, it's doing one thing that's very important. As with any continuous symmetry, the presence of this continuous U1 symmetry of the Dirac Lagrangian leads to the presence of a conserved current. What theorem is that every continuous symmetry leads to a conserved current?
The Noether's theorem.
Noether's theorem. I'm sure you're pronouncing it better than I am. Yes, exactly. So because there exists this symmetry, we are guaranteed by Noether's theorem that there exists a conserved current that goes along with it. This symmetry creates a conserved current. So I can find that by setting the variation of the Lagrangian to 0 because this is a symmetry, and that variation of the Lagrangian comes because of the variation of the field plus the variation of the field psi bar plus the variation with respect to the gradients. And if I do the usual manipulations, I plug in the equations of motion. I get d mu of variation of the Lagrangian with respect to the gradient, d mu psi delta psi. And if I plug in the infinitesimal transformation that gives me this U1 phase rotation, then I find what that conserved current is. I get 0 equals d mu of psi bar gamma mu psi. So this tells us that there exists a conserved current such that d mu j mu equals 0, and that current for QED is psi bar gamma mu psi. This is essentially I would say b dagger b minus d dagger d. It counts the number of particles minus antiparticles that are flowing in a particular direction. If you take this particle number current and you add to it the electric charge, then you get the electromagnetic current, which would be E psi bar gamma mu psi. So that's step one. The free Dirac-Lagrangian possesses this happy little symmetry, and that happy little symmetry guarantees a happy little conserved current, and everyone is happy. Why is a conserved current useful? The conserved current is what makes it possible to bring in the photon. So if the essential trick of gauge symmetry is to turn the scalar mode into a symmetry operation, turn the addition of a scalar mode into a symmetry. So that means I want to take my gauge field, A mu, and transform it to a new A prime mu, which is equal to the old field plus a scalar polarized mode. So I can think of this as I'm starting in a perfectly good physical configuration and then trying to screw it up by adding in one of those toxic scalar polarized modes. What impact will this have on my Lagrangian? My Lagrangian has free pieces, kinetic energies, but what about the interaction? The interaction part of my Lagrangian will bring in that vector field somehow. It's got to have an A mu in it if it's going to create photons, create A mu. I've got a vector that is being created, and I've got to have a scalar on the left, so this has to come with some kind of other vector, some kind of current that creates it. If I want this to be a symmetry of the interaction Lagrangian, then when I transform L to L prime, right, so this is J mu A prime mu, which is J mu A mu plus D mu phi. So this is my old interaction Lagrangian, J mu A mu plus J mu D mu phi. The whole essence of the trick is I'm going to interchange the order of the derivatives and use product. So this is L interaction plus the total derivative mu of J mu times phi minus the product in the other order, phi times d mu of J mu. So if I have anything, something that creates these photons, and I want to make the scalar mode a symmetry, I'm almost there. When I add this extra scalar mode, I get something which is a total derivative. That's good. The total derivative is an irrelevant shift in the Lagrangian. It just becomes a boundary term on the action. It's like adding a constant, so it doesn't affect the equations of motion. So this part is good. This part is a symmetry of the Lagrangian, but only if this last term goes away. And what does it take to make this a symmetry of the Lagrangian? It requires b mu j mu equals 0. So I can do exactly what I want with an interaction vertex of the form j mu a mu for any conserved current. As long as d mu j mu is equal to 0, I can use j dot a as the form of my interaction vertex. That will solve my problem and turn the addition of this stupid scalar mode into an irrelevant total derivative that has no impact on the physics. So essentially what I'm saying is that I can start with the free Dirac Lagrangian and just add to it J mu A mu by hand. So let me call that the gauged Lagrangian. So that would be psi bar I d slash minus m psi, and now I'm going to add in that external current. Let me write it here in the form which includes the electric charge. So minus E psi bar gamma mu psi A mu. It's quite remarkable that this generalization looks just like I've replaced the derivative with something. I have the same psi bar, I have the same psi. The only thing is that now this term is minus psi bar E A slash psi. And I can group that in here. So this is psi bar ID slash minus M minus E A slash. And I can combine that E A slash with the ID slash. So this is I times D slash plus I E A slash minus M psi. So this trick of adding in J mu A mu actually at the end of the day looks just like I took my partial derivative and I expanded it. It looks like I took d mu and replaced it by the gauge covariant derivative capital D mu, which is d mu plus IE A mu. If I take any time I have this in my free Lagrangian and I promote it, this action is equivalent to adding in that sacred form to your interaction vertex in the form of a conserved. This procedure is known as minimal coupling. And this D is the gauge covariant derivative. So what does that do? Now let me go back to the full QED Lagrangian and see what happens when I perform that local transformation now. So the result of adding minus J mu A mu or minimal coupling is the extension of the gauge symmetry. From global to local. So what I mean specifically is now if I have the full Lagrangian, and now I perform this transformation, so psi prime of x is e to the I theta of x. It's now allowed to vary by spacetime. Psi of x, so similarly psi r prime of x is e to the plus I theta of, e to the minus I theta of x. Psi of x. Right. So if I substitute this transformation in, the non-trivial part comes from when the derivative acts on that phase. Before, if the derivative commutes past the phase and it acts on the field, then I just trivially get the cancellation of e to the I theta and e to the minus I theta. So when I do this, my new Lagrangian, the transform Lagrangian equals the old Lagrangian plus the extra term. That extra term is psi bar id slash acting on e to the I theta of x. Psi. Plus the interaction term, so minus e psi bar gamma mu psi, and then have a psi mu, whatever my transformed field is. So let's see, when I take this derivative, I bring down psi bar gamma mu psi. And what I'm left with is a factor of minus d mu theta. Yes, minus d mu theta. Yes, exactly. And when I put this back together, this extra term, it has exactly the same form as this. And what does it look like? It looks like this extra piece, as a result of my local transformation, is adding on a scalar polarized mode to A mu. So this transformation gives L prime equals, let me write it all out in thing. Psi bar id slash minus m psi minus e psi bar gamma mu psi A mu prime plus 1 over e mu theta. And I think I still need to put in that energy. So the point that I'm trying to make here is that the result of doing all of these things together is that we have now linked together the symmetry transformation that we started off with and the scalar mode of the vector field. These things are now equivalent. If I perform a local transformation of the Lagrangian, the effect is I just added a scalar mode to A mu. And the other way around. So now if I start off with an A mu and I add the dangerous scalar polarized mode, that scalar polarized mode is just equivalent to multiplying your field by an overall phase. So the dangerous scalar mode now becomes irrelevant or unphysical because it just goes into redefining your fields, redefining the that's the magic of gauge symmetry. So if I can try to articulate the logic and how it flows, the thing that begins it all is the global symmetry of your free Lagrangian. The starting point was the Dirac Lagrangian, psi bar id slash minus m psi, and the observation that it possesses U1 symmetry, global symmetry. Under the redefinition, psi prime is e to the I theta psi. The fact that I have such a symmetry is what gives me the existence of a conserved current in the first place. This tells me d mu, j mu is equal to 0 with, for this theory, the particular j mu psi bar gamma mu psi. It's perfectly fine to stop here. This is the property of the free Dirac theory. But what does it mean to have a gauge theory? It means to take that symmetry and to use it as the basis for defining a vector boson. This is the only way that a massless vector boson can exist. It cannot exist on its own. Without this, there is no photon. Without the interaction of the photon with matter, there is no photon. It needs this to protect itself against the scalar polarized mode. So if you want to use this to define a vector field, you define a mu using this symmetry. And the way that you do that is by minimal coupling. You promote the partial derivative to the gauge covariant derivative, which is equivalent to adding an interaction vertex of the form minus J mu A mu, where this J mu is the conserved current that came from the existence of the global symmetry. As a result of doing this, what you effectively do is you complete or extend the gauge group. This now generates the local U1 symmetry. But the meaning of this symmetry is now significantly different. The global symmetry was a property of the fermions alone. The local symmetry is a property of the fermions together with their specific interaction with the photons. The two collaborate together in order to use this symmetry as the basis for the photon. The implication for this in my mind is that when you are doing field theory, when we are doing a gauge theory, we are working on more than just space-time. We are also working in this gauge dimension at the same time. So the point that comes out of this is that we are adding an unphysical gauge dimension to the manifold on which we do our theory. So if I can switch to sharing screen for a moment to illustrate what I have in mind. There we go. What I'm trying to say is that when you are working with a gauge theory, you can no longer just think about space-time, about the dependence of your fields on space-time. The behavior of your fields in space-time is now inextricably linked together with their behavior in the gauge dimension. So I imagine that in addition to my space-time directions, which are represented here on this plane, that there's also a new orthogonal direction of my manifold on which I'm doing my theory that describes what gauge I'm in. So I can imagine, just for specific sake, a family of gauges similar to covariant gauge. So I can have d mu a mu equals 0, d mu a mu equals +1, d mu a mu equals -1, and I could have a whole axis that defines a continuous family of gauges. That's just one of an infinite number of ways to describe what those gauges might look like, but it gets the idea across. So the point is that when you are working with a gauge theory, you are working with something that lives both in space-time and in gauge directions together. And those two dependencies can talk to each other. So it really starts to look like you are doing derivatives on a curved space, even though space-time itself is flat. The space-time directions themselves are flat. There's no curvature here. But there may be curvature, quote unquote, in the gauge direction. What I mean is what I'm trying to illustrate here in the figure, that I might have some function in the gauge direction that changes as I move around in space. That would be like a Christoffel symbol that measures the derivative of a gauge quantity in the space-time directions. That can be non-zero, even though the space-time directions themselves are. So it helps to really bring in the language here of working on a curved space to describe what this gauge direction is doing. By the way, I was struck by a particular sentence in Weinberg's textbook when he was discussing this. He shows nicely that the photon itself is not Lorentz invariant. If you start with a photon field for a massless photon, and you try to transform it so it lies on that space-time sheet, blue space-time sheet, you can't. If you take the photon at one point and you boost it to another point, it changes its gauge. So that's just another illustration of the fact that in order for the photon to exist at all, you have to augment your space-time with this gauge dimension, and you have to work in this enlarged space for your theory. Okay, so that is the most precise answer that I know how to give you to what is a gauge theory. A gauge theory is a very particular type of Lagrangian which uses symmetry as a governing principle to not only dictate a conserved current, but to use it as the basis for defining a vector field, a gauge field that goes along with it. Those two things are always fundamentally interconnected. Okay, so in my remaining 30 minutes or so, I wanted to just wrap up that discussion of the geometric interpretation.
Could I quickly just ask a question?
Yes, please.
I have a feeling I don't fully understand how you're saying as we move through space-time, the gauge can change, but I don't see how that comes about in the Lagrangians that we've set up. It seems like we've just introduced certain terms in order to establish this local symmetry, but I don't understand what the gauge part of that comes into play.
The picture that I'm drawing is sort of me grasping for a way to visualize the math that I'm going to show you now. It seems like it's the language of describing, derivatives in curved dimensions, much like general relativity, except the direction that we're talking about is the gauge direction. It's the effect under a gauge transformation. So it's possible that I'm not saying things in the most technically clear way, but that's what I'm trying to articulate, is that we are, in order for this theory to make sense, you have to have a gauge transformation be an unphysical effect, so that it doesn't matter. It doesn't matter if in boosting from point A to point B, I accidentally changed gauge in the process. That is okay, and that has no physical consequences, and that is necessary. That is something that actually happens if you take the photon field and you perform a Lorentz transformation. So, I don't know, I haven't shown that particular feature of it, so I don't know how to show that to you in a straightforward way.
Okay, I can wait.
Yeah, I'll have to think about how to elaborate on it more. It's possible that I'm grasping for something and I'm not visualizing it precisely, but I think it's something close to this. So maybe let me illustrate the sort of the definitions of covariant derivative and see if that maybe gives a suggestion for what the more correct interpretation. So the idea is that the covariant derivative is a special generalization of partial derivative. So I have the partial d mu, and then I have the covariant derivative d mu, which is partial mu plus I e a. And the thing that's nice about it is that if I make the combined transformation that we just saw, psi prime is e to the I theta of x psi, and a mu prime equals a mu minus 1 over e mu theta. Then the partial derivative does not transform simply. Right? If I have d mu psi prime, then this would be d mu of e to the I theta psi, and that's going to give me e to the I theta of d mu psi plus, I think I can flip that here, plus I d mu theta psi. So this does not have a simple transformation. The thing that the covariant derivative does is that it compensates for this extra term. So it comes to this. The transform covariant derivative would be d mu plus I a mu prime psi prime. So this is d mu plus i.e. the old a mu, and then under this transformation, I get minus I d mu theta. Times e to the I theta psi. And now these two things exactly compensate for each other. So I have d mu plus i.e. a mu minus, when this derivative acts on psi, I get the e to the I theta comes through. The I theta, and then when the derivative acts on the theta, I get the plus I d mu theta psi that cancels this. On the side. So the point is that the extra transformation of a mu by unshifting that scalar mode cancels out the extra contribution. And I just get e to the I theta d mu psi. So the idea is that your standard derivative is an unfair comparison. That if I take a derivative on something that may be gauge transformed, maybe this is the point in answer to your question. The local gauge transformation behaves differently at every point in space. That's the connection. So if I'm allowed to make a different gauge transformation everywhere in space, then that affects the space-time. So the difference in my gauge transformation at different points. So that dependence of theta on x, the different transformation that I make at different points in space, changes the nature of the derivative. It adds this extra piece from the unequal gauge transformations at different spaces. What does the covariant derivative do? It compensates for that. It undoes that change coming from the unequal gauge transformation problem. So this really starts to resemble, I don't know, parallel transport on a sphere. I have something that was a derivative, it was supposed to be going in a particular direction, and I want to move it around from space-time point x to space-time point y. The problem is that when I transported it, my direction got changed. It's very analogous to this, and the reason for it is because I can make a different phase rotation at every point in space. So in exactly the same way that parallel transport is complicated, you need to define a modified derivative that compensates for the curvature of your space. That seems to be exactly what's happening here. Your gauge covariant derivative is compensating for the different gauge transformations that you made at your starting point and your ending. I think that's probably the better way to say what I was trying to say. This further lends itself to a nice interpretation of the kinetic energy that will be very helpful when we want to construct QCD tomorrow. It means that I can write the field strength tensor as a commutator of the covariant derivatives. Nice interpretation of F mu nu as parallel transport. If I have this idea of moving around in space-time where I might have funny parallel transport effects due to different gauge transformations, I can basically move around in a plaquette, move around on a square, and I can look at the effect of taking a derivative in one direction and then each of the others. So I can sort of take a step forward, across, back, and around. This quantity would be described by the commutator of the covariant derivative. So if I have a particular direction mu, which is this way, and a particular direction nu, which is this way, this commutator measures the inequality, sort of what is the total effect of starting with a particular direction, transporting it all the way around and looking at where I end up. That's that measure of this commutator, the difference between going right and then up versus going up and then right. This object, if you calculate it out, is IE times mu a nu minus d nu a nu. And this is just IE f mu. So for our original purposes, it was fine just to say f mu nu is defined to be d mu a nu minus d nu a mu. But perhaps a deeper definition is to say f mu nu is minus I over E commutator of the covariant derivatives. That this is f mu nu as sort of the curl, if you like, the total amount of rotation as you go around this parallel transport loop under the influence of the gauge transformation. This is a form that will generalize very nicely when we want to calculate the field strength tensor for QCD, because now we can define the covariant derivative and then use the impact of the covariant derivative to calculate the numeric. Okay, I think that's the end of the notes that I had planned to cover today. How much time do we have? Still got another good 20 minutes. So I would say the main point of this discussion is that massless vector bosons are susceptible to the scalar mode. Gauge symmetry renders them harmless. It makes them harmless symmetry transformations. And that's for a specific form of the interaction vertex. And in the process, when you are doing this, you are effectively enlarging the symmetry and enlarging your manifold that you're working on for your theory, enlarging the symmetry group from global U1 transformations to local U1 transformations that allow different gauge transformations at different points in space. And this effectively enlarges the space for your theory. It is now space-time plus gauge degrees of freedom. And this sort of has a natural interpretation in the language of curved space. So that is a geometric interpretation. So the plan from here is to continue with the construction of QCD. Now that we've really popped the hood on quantum electrodynamics to see how is it constructed, how does it work, why is it built this way, now it is a straightforward exercise from step 1 to step n to gauge QCD. To start off with quarks that have 3 different fundamental colors, and now a conserved current that allows me to rotate between those different color states in different ways. And once we identify what is the global symmetry, then we can just proceed to promote it to a gauge symmetry and obtain the QCD Lagrangian straightforward. So why don't I stop here? Are there any questions that we can discuss? I'd be really hesitant to launch into something brand new in the last 15, 20 minutes.
There are questions.
So I'm just trying to make sure I understand this manifold interpretation correctly. So can I interpret this new gauge dimension, as you mentioned, as you call it, just as a fiber bundle on our spacetime?
The answer is
Ooh,
yes.
That's a technical term that I don't know the answer to, but it sounds useful.
Yeah.
We should discuss.
Yeah, the answer is yes. And if you,
Cool.
there is a very strong analogy with, well, with the frame bundle description, say, of general relativity. Because if you look at this commutator that you see there in the definition of F mu nu, if you play the same game in general relativity, you would take commutators of general relativity covariant derivatives and get the Riemann tensor out, right? Now, the Riemann tensor, of course, has 4 indices. You only see 2 there. The trick there is that the 2 of these indices on the Riemann tensor are the analogy of what you're going to see next time around in the essentially group indices or Lie algebra indices that appear in the non-abelian. So you see 2 of these indices only here because the Lie algebra is one-dimensional. There is no, there are no indices to talk about. It's just one number. That's sort of the match. But you have to go essentially. So if you go into frame bundle description of general relativity, then that really almost directly maps onto the fiber bundle description that you have, that mathematicians use to introduce this.
That's really cool. My differential geometry isn't strong enough to have that level discussion, but I would love to know more. That's really
I hope they're not asked more in the Dutch session.
All right, good.
I do just have a question. So, I guess just for clarification of why does having a mass allow us to get rid of the scalar polarization? I know it gives us that constraint, but how does that constraint get rid of that polarization?
It's a very subtle question. I think the ultimate answer is that there's a phase transition associated with whether the mass is 0 or the mass is non-zero. So that if you're in the massive phase, that you have sort of an explicitly broken symmetry because of the presence of the mass. But if you are in the massless phase, then you have a spontaneously, I don't know if that's the right phrase for it, spontaneously broken symmetry. It's not broken. I guess picking a particular gauge would be breaking this. Maybe I can turn it around because I know the answer for the case of BCS superconductivity. The beautiful analog to BCS is that the superconducting state is what you get when you have exactly spontaneous breaking of U1 gauge symmetry of QED, as we discussed here. And what does that do? It takes the massless photon and it turns it into a massive photon. It's something now that doesn't propagate for an infinite distance like it does in vacuum. In a superconductor, it has a finite decay length, the London penetration depth. And 1 over the penetration depth is just the mass of the heavy photon in that case. So what I know is true is that if you start in the unbroken gauge symmetry and you break gauge symmetry spontaneously, then you generate this. And in the massive state, you've broken gauge symmetry explicitly. You've essentially picked the gauge, so to speak. So I think that's the deep answer, as best I understand it, that the mechanism by which this symmetry is addressed is very different in the massive and the massless limits, and that let's say the massless limit is not smooth. If you start with the massive theory and you try to take the mass to 0, instead you hit a phase transition that happens exactly at m equals 0, which is where this gauge symmetry shows up. So I think that's the best answer that I can give you, that the symmetry appears to be explicitly broken when you have a mass, so that you have explicitly a constraint that forbids you from ever having the scalar polarized mode. But if you're below the massive phase transition so that the theory is massless, now that's all wrapped up in the symmetry group itself.
Okay.
Does that help?
Yeah.
Okay. Anything else we can discuss? I'm really not inclined to try and start a new discussion here in the last 10, 15 minutes.
Well, I have a question on your discussion of the resummation.
Sorry, the question about what?
The resummation.
The resummation, yes.
So what exactly is being done here? So firstly, we say this is an asymptotic series, right? So you have something that's
Yep.
and then it seems like you choose to pick part of the series, right?
Yes, that's exactly right. We're
And-
picking out a
but-
specific subset of that series to resub. Yes.
But you say all of those terms of order one, so that doesn't converge either.
I'm sorry, I can't hear you very well. Can you say that part again?
All the terms you're adding are of order one.
Yes, all of the terms are of order one. That's correct. So
The
when
new object, the new series you have doesn't converge either.
that's where I get lucky. Most of the perturbation series do not converge, but this particular one does, and I know what it converges to. Essentially, what I have is I have a superposition of terms that look like alpha s log qs squared over mu squared to the power n. And I'm summing these up from n equals 0 to infinity. And if I think about the combinatorics, there's probably going to be a 1 over n factorial that comes in. The answer is that the result is just an exponentiation of that resummation parameter. So I'm saved here because the exponential series is everywhere convergent. That particular series is convergent, even though the full asymptotics, the full series of alpha s is only asymptotic. So the result of exponentiating this thing, of course, e to the alpha s log q squared over mu squared is the same thing as e to the log to the power alpha s. And then e to the log cancels each other. So what this does is it gives you power law behavior. And then, I don't know, there's usually some coefficients that go along with this. The result of summing these things up is you get alpha s times some number. You have to actually solve the differential equation and compute exactly what that number is. But this is sort of the nature of the resummation. You're doing an exponentiation of n number of insertions of exactly the same factors. So you know what it ends up being. And because of that compensation between the exponential and the log that you started off with, that typically gives you sort of power law behavior. For us, the point that I'm going to be getting towards is that when I do this resummation and I have logs of 1 over Bjorken x, this translates in exactly the same way to powers of 1 over Bjorken x. You get 1 over Bjorken x to the power alpha s times. Does that help? I think I see your point about, I told you that I can't sum the series and then I summed the series.
Yeah.
But I think this particular series is maybe the only one that I know for sure I can sum.
All right, good. It's very clear.
Thank you.
Maybe an extra comment. You're essentially shifting the starting point of your perturbative series, because right now, with all these order one terms resummed, this is now your lowest order, 0th order, essentially.
Exactly.
And then corrections come from terms that have powers of alpha in excess of number of logarithms. So next to leading order would be something that contains an extra alpha s times an arbitrary power of alpha s times the log in question. So you reorganize your perturbation theory around a different place, right? Where you, well, in your dynamical description of a variable. Yep, Matt's about to write this down explicitly.
Okay, yeah, sorry, I'm trying to sort of sketch the whole competition of terms and how one sums them up. So let me see if this helps. So as far as the log resummation, you start off with a perturbation series that's organized like this, where it's all just counting powers of alpha s to the 0, alpha s to the 1, alpha s to the 2. But now I imagine that inside this term that multiplies alpha s, not everyone is created equal. Part of this cross-section comes with a systematic log, and part of it doesn't. And then when I go to second order, I have the opportunity to make up to 2 logs. So there's a part of this that has both of the logs. There's a part of it that only has 1 log, and now there's a part of it that doesn't have any logs. And I can keep going on further down the series here. The point is that I want to regroup these terms when alpha s times the log is of order 1. So I'm going to regroup these terms, and now my d sigma 0 is competitive with this. This piece has an alpha s and a log, but alpha s log is order 1. So this is d sigma 0 plus alpha s log mu squared over mu squared d sigma 1 comma 1. There's also a leading piece out of this one. That's the part where I have the maximum number of logs. 2 alpha s's, 2 logs. Alpha s squared q squared over mu squared d sigma 2. And in principle, I have an infinite number of these terms where I have 0 alphas and 0 logs, 1 alpha and 1 log, 2 alphas and 2 logs, and this thing is all terms that have equal numbers of alphas and equal numbers of logs. All of this stuff is order 1. So part of what Herbert is saying is that we've changed what the leading part of the perturbation answer is. Before, this was my ground state, quote unquote, the lowest order answer. Now, after resumming, all of this is the new 0 after resummation. But I can still correct it systematically order by order. If this is my leading term, this is called leading log term. So this is d sigma leading log approximation. That's this one. But then I also have all of the terms that are higher. I have something like this, where I have 1 alpha and no logs. That's just small. I have a similar term here. Here I have 2 alpha s's, but only 1 of the logs. So I can have something like d sigma 1 comma 0 plus alpha s log q squared over mu squared d sigma 2 comma 1. Stop. These are all of the terms that have 1 extra alpha s compared to the number of logs they have. So these terms are the ones that have alpha s to the n plus 1 log to the n. These terms are smaller than these ones. These terms are order 1, these terms are order alpha s. And so you see, I still get a controlled expansion, but I've changed which terms go where in that power cap. So now, as a result of doing this summation, now I get the leading log, which is all of this stuff in brackets, plus alpha s corrections times next to leading log. And if I continue the same thing, then I would have all things that have 2 extra alpha s's, no matter how many order 1 combinations of logs. So the point is that this is everything which is order alpha to the n log to the n. This is everything which is alpha to the n plus 1 log to the n. This is everything which is alpha to the n plus 2 log to the n. And so I've got a whole new series of alpha to the n plus m log n's. I've got a series of these things, which is control. Does that make sense?
And now it's the m that controls how much it is suppressed, right? The excess alphas.
So I sort of have all of the same terms that I always had. It's exactly the same series, but I've reorganized it to say now, if q squared is large enough, then this is no longer my starting point. If q squared is sufficiently large, this is the new starting point. And that sort of reorganizes all of those terms.
And then that is asymptotic as well again.
It is probably asymptotic as well again, but you have reorganized where it is good, right? The thing with asymptotic series, you can do fantastic things with them by reorganizing them, right? It doesn't converge anyway. So, but you can sometimes, if you write down a series carelessly, it wouldn't converge, right? But if you carefully reorder the contributions in a particular way, you could turn it into a convergent series. Right? You heard the funny thing about summing all the integers, 1 plus 2 plus 3 plus getting -1/12. Right? That's part of the game. The question is whether it makes physics sense in this case.
So why does one not run into Riemann's theorem that you can, if you rearrange a divergent series, you can get arbitrary result?
You need a physics statement to say to judge whether you've actually made physics sense in the end with your rearranged series.
So you get an arbitrary result, but one of these arbitrary results is physically meaningful.
Exactly, and then you need an external criterion.
Then we can just sum the harmonic series every time. Just change.
So asymptotic series is more well studied than that. Right?
Yeah.
So you know, it's a well-defined area of mathematics to study asymptotic series. Saying I'm expanding in a certain thing, and like certain things are large, it's a whole technical language. But the thing that gets tricky where it's a bit more art is at what point does the asymptotic series no longer describe what you're trying to describe? And
Right.
Sort of the naive result is kind of the common one, which basically you add terms until it goes bad. So like you at some point it's going to diverge, but you don't necessarily know when that's going to happen. So a common thing to do is you add terms until your next term is as big as your previous one. It converges until it diverges. Okay. So it's definitely not like adding the integers graph.
So I guess maybe my 2 cents on the takeaway for this for all of the students is whenever you listen to a scientific talk and they show you their favorite high order calculation, always double check how big is NLO compared to LL? How big is the correction compared to the lower order? If they're not getting smaller, your series is not converging, then you should start to be worried.
Sorry, I've got one more question. If we just go back to the blackboard.
Yes, please.
So when you first expand the differential cross section, expand it in terms of powers of alpha s.
Yes.
And I'm assuming that the superscript refers to the loop order of the differential cross section.
Yes, that's right. This is just a notation to keep track of which function multiplies which power of s. Yes.
Right. But when you expand it in the next line,
Yes. Now
it is a double superscript notation. I was just wondering what each of those what the notation actually denotes.
Yeah, so I just sort of made this up on the fly, but I was writing, let's say d sigma nm is something that has alpha s to the power n and log to the power m. So this term, the 1, 1, is something that has 1 alpha s and 1 log. The 1, 0 has 1 alpha s but 0 logs.
Okay.
I don't think there's anything particularly special about it. It's just the notation I came up with.
Looks like we're good. Well, thank you. Thanks, Matt.
Excellent. Thank you guys very much. Just wait tomorrow with constructing QCD and calculating things with it. Enjoy the rest of your day.
You too. Get a good night's sleep.
Thank you. My office is very comfy.